Um, Hello everyone, my name is Xingchen. So I worked at Imperial when I submitted this presentation, but recently I joined Exit as a senior lecturer. So today I'm going to talk about our research on object tracking. So the title is Self-Supervised RGBT Tracking with Cross-Input Consistency. So firstly, this work is about single object tracking. So in this task, we know the position and the size of the target in the first frame, when we hope to track this target in subsequent frames. This is actually a very typical computer vision task, and many good methods have been proposed so far. But most trackers are based on RGB images. The problem of RGB images is that when the lighting condition is very poor, or when there is heavy smoke in the scene, we cannot see the people very clearly in these images. So in this case, the tracking may fail. For example, in this video, in the tunnel, the lighting condition is very bad, so the tracking performance is not good. But if we consider another kind of images, for example, the thermal image, because the thermal cameras use different wavelengths when in the process of image forming, so it can detect the heat radiation from objects. So in this case, even when the lighting condition is very poor, or when there is heavy smoke, we can still see the people very clearly in these images. I have shown some examples where thermal images are better, but also there are some other cases where RGB images are better, because RGB images can provide more details. For example, the color information, so which is also very important for tracking. So in this sense, the RGB and thermal images are complementary. This is why, in recent years, more and more people are trying to use both RGB and thermal videos in tracking to perform the multimodal tracking. In this figure, I list the performance of main RGBT trackers on the public dataset. So as you can see, most of these trackers, they require a large number of annotated data for training. And also, because the training process, the labeling process is time-consuming and expensive, so we hope to avoid this. So in this paper, in this work, actually, we aim to develop a deep learning-based RGBT tracker without using any human annotations. So in this famous self-supervised learning framework, usually the augmented views from the same image are generated in a training process. They compute the similarity as a loss function to train the framework. Inspired by this idea, and also inspired by my real life, so so given consider the current famous self-supervised learning framework. So I thought about how I can use the unlabeled RGB and thermal video pairs to build these multiple views to train our tracker. Previously, when I worked at Imperial, so every day I went from my department, the EEE, to my wife's department, aeronautics. So sometimes I went through the main entrance of the college, and sometimes I use another way, another road. So I found that use both ways, I can arrive at the same destination. So actually, inspired by this idea, I proposed a cross-input consistency. So the basic idea is we can perform the tracking, use different inputs. So actually, I propose two ways to construct cross-input consistency. The first way is we can actually track the object using different modalities. For example, we can use the RGB videos. We can also track the object using the thermal videos. The second way is we can actually use different routes to perform the tracking. For example, we can track the object from frame T to frame T+1 and then to T+2. But we can also track the object from frame T directly to frame T+2. So ideally, we should have consistent tracking results at frame T+2. So for the first idea, actually, I have tried different combinations of the modalities. So far, I find that when I use two branches and also use the first branch, use the RGB images in the first branch, and use a combination of RGB ensemble in the second branch, I can have the better performance. So this is our training framework. So basically, we are using a correlation filter-based framework. So we firstly use CNN to extract features, and then we do we use a correlation filter to compute the response map. So in our training in our training stage, we use the same initial label, which is Gaussian label, for both trackers, and then we can generate two response maps from these two trackers. We then compute cross-input consistency based on these two response maps. So using this loss function, we can train these two trackers together. And then after training, we use only the RGBT tracker in the for tracking. Another important thing in this idea is how to generate the training data without using any annotations. So actually, I used the idea from a previous paper. They simply use the center patch of each image. So the basic idea is we crop the center patch of all the original images and resize them. So in this case, we can have a series of center patches from the original video. And then we select the first frame as our template for tracking, and we randomly select another patch from the remaining 9 frames for as our search plate, and then we feed both the template and the search place to our training framework for training. So in this case, we don't need any human annotations to generate the training data. In our experiments, actually, we use 2 public data sets in this field to test our idea, and also we use 2 common metrics to evaluate our method. So this is the performance comparison between our method with the supervised trackers. So as you can see, without using any human annotations, our method opt from 7 supervised trackers. Although there is still a gap between our method with the state-of-art supervised trackers, these trackers, they all require a larger number of annotated data. The second thing is because they use a large model, so the tracking speed of most trackers are very slow. For example, 1 FPS or even 2, something like that. So most of trackers, they cannot satisfy they cannot meet the real-time tracking requirements. But because we are using a lightweight backbone, so our tracker is very fast. It can reach 180 FPM frames per second. I also compared our idea with supervised training. So an interesting finding is that on the GTOT dataset, our self-supervised training is more effective than the supervised training. So the possible reason of this is that when we only use the center patch from the training set, we can generate more diverse data compared to the ground truth bounding box. But when we use a small data set to train and test the result on a larger data set, I mean, there's still a gap between our method with the supervised training. And also, in object tracking field, there is a famous loss function called cycle consistency. So the basic idea is we firstly do the tracking in a forward way, and then we do the tracking in a backward way. So we can compare the cycle consistency as shown in the right figure. So I also compared our cross-input consistency with this cycle consistency. So as you can see from the table, our cross-input consistency is more effective than the cycle consistency. The main reason is, I think the main reason is, in some cases, the tracking cannot be performed in a backward way. For example, when there is heavy occlusion, the backward tracking may not be successful. So in this case, the cycle consistency is not very effective. So in general, because we only use a forward tracking process in our cross-input consistency, so it can handle more challenging cases compared to the cycle consistency. And also, I propose another way to construct cross-input consistency. As I mentioned, we can track the object using different rules. So in this case, I'm using in the first branch, I'm using all three frames in the training process. But in the second branch, we track the object from the first frame directly to the frame t+2. So in this case, I can also compute the cross-input consistency. So as shown in the table here, this idea is not as effective as the first one, but still is slightly better than the cycle consistency training. So this is the demo of our tracker. So as you can see, sometimes the RGB tracker fails, sometimes the thermal tracker fails, but our self-supervised RGBT tracker can track this all these targets very well. So I will show them again. So actually, our tracker is more robust. Considering the different lighting conditions or some other factors that's affecting the tracking performance of either RGB tracker or thermal tracker. So in conclusion, so from our study, we found that self-supervised RGB tracking is possible, and also the cross-input consistency is a very effective way to achieve this kind of self-supervised learning. And using only a very lightweight backbone and no human annotations, our tracker outperforms 7 supervised trackers on public datasets. And also, I think this idea is generic, so it can be extended to other modalities, for example, RGB and depth. So actually, we are working on this idea to do more exploration. Thanks so much.
Great. We have time for short questions. Any questions?
No. The thermal camera, they were separate, and then you did registration between the data from the thermal to RGB?
Yes, registration is important, but I'm using the public dataset, so they already did that.
Okay, great. Let's thank our speaker again.